Welcome back. We're now starting the second module where we will talk about the control and data plane separation. By the end of the module, you should be able to explain the difference between the control and data planes, as well as the functions of each of them, including the infrastructure that's required to support each of the control and data plane. We'll also talk about the challenges of separating the control and data plane and various approaches that have been taken to tackling these challenges. The module comprises 3 lessons. The first lesson is the overview, where we'll discuss what control data plane separation is, why it's a good idea, and we'll provide a brief overview of the opportunities and challenges of separating the control and data plane. The second lesson will discuss opportunities in more detail, and the third will talk about challenges and approaches to tackling those challenges. So first, what are the control and data planes? The control plane is logic that controls the forwarding behavior in the network. Examples of the control plane are routing protocols, network middlebox configuration such as firewall configuration or load balancer configuration, and so forth. One can think of it in some ways as the brain of the network. The data plane, on the other hand, forwards traffic according to the control plane logic. Examples of data planes are IP forwarding, layer 2 switching, and so forth. The data plane is sometimes implemented in hardware, but also is increasingly implemented in things like software routers. So why separate the data plane and the control plane? One reason is that by separating the data plane and control plane, each can evolve and be developed independently. In particular, the software control of the network can evolve independently of the hardware. That means one can buy routers, switches, middle boxes, and so forth, deploy them in the network, and not be bound by the capabilities of software that ship with the hardware at that particular time. A second reason to separate the control and data planes is that it allows the network to be controlled from a single high-level software program. So higher order programs could control the behavior of the entire network. And in doing so, not only is it easier to reason about the behavior of the network, but it's also easier to debug and check this behavior. So there are various opportunities that we'll look at where separation actually helps. In this particular lecture, I will provide a brief overview of where separating the data and control plane can help in data centers and in routing. And in a subsequent lecture, we will talk about also where this control and data plane separation can help make certain applications in enterprise networks easier to manage. We'll also talk about how the separation of control and data plane can help in research networks by allowing research networks to coexist with production networks on the same physical infrastructure. One particular domain where separating the control and data planes has proved particularly useful is the data center, where it's relatively commonplace to need to move a virtual machine from one physical location in the data center to another as traffic demands shift. As one example, Yahoo cites that it has about 20,000 servers in a cluster in a data center, resulting in about 400,000 virtual machines, each of which might need to communicate with any other virtual machine, thus resulting in about 1,024 distinct interhost links between any pair of virtual machines for the topology that they've deployed. Now, if on top of that you want to guarantee sub-second virtual machine migration and guaranteed consistency in the network as that migration occurs, this problem becomes particularly hairy. The solution to this problem that Yahoo has taken is to program each of the network switches from a central database. So as virtual machines migrate, that central controller knows about the migration and can update the switch state accordingly so that network paths update in accordance with the virtual machine migration. As another example, suppose that an attacker is sending denial of service attack traffic to a victim. In this case, it can sometimes be difficult to squelch that traffic near the source. One approach that AT&T has taken is to separate the data plane, or the routers that forward that traffic, from the control plane that makes decisions about what to do with particular traffic flows. In particular, they've deployed something called the IRSCP, which is a commercial version of the RCP, which we've talked about. which will insert a null route into a router for particular flows or destinations that are receiving attack traffic. So those are just two examples of how the control and data plane separation have helped in specific cases, but there are also challenges to making the control and data plane separation a reality. The first is scalability. Once you separate the control elements from the forwarding elements, it's likely that a control element may be responsible for many forwarding elements, and sometimes thousands of forwarding elements. The other challenge is reliability or security. What happens if a controller fails or is compromised? Well, we should hope that the forwarding elements continue forwarding traffic, business as usual. But once we've separated the brains of the network from the devices that are actually forwarding the traffic, correct behavior is no longer guaranteed if a controller should fail or be compromised. So in the coming two lessons, we'll talk about both the opportunities and challenges associated with separating the data and control planes.